Hello, folks. Everybody could get seated. We're going to get started, and I don't know if somebody's going to go in the hallway and tell people we're moving, but I want to get started. I'm the moderator for this session, and our first speaker is Jon Taylor. Over 20 years experience in the semiconductor industry, lots of work in verification, embedded software with ARM, and now RISC-V. He has a degree from Southampton University in electrical engineering, and he's currently the director of product technology for Imperas. So let's welcome him, and he's going to talk about RISC-V verification ecosystem. So,
thanks, Mark. So good morning, everyone. Welcome back. Hope you're all full of coffee and cake and ready to keep going through till lunchtime. As Mark said, I want to talk a little bit about verification ecosystem this morning. And we've heard a lot about ecosystem already, both from Mark and from Calista. And they talk mostly about the software ecosystem and the hardware ecosystem for RISC-V. But I think there's a third pillar to that that's just as important, but perhaps a little more understated, and that's verification ecosystem. And so I'm going to talk today about the importance of that, some of the work Imperas has been doing around open standards, and some of the tooling and changes we're all going to need to be successful to make RISC-V the massive success it should be. So again, Mark touched on this a little bit earlier, but spoiler alert, RISC-V, it's not a processor, it's not open source, it's not free, it's an open standard, but we think there's a real risk of a disconnect, of it failing if we don't get the verification story right. It's always hard to think about verification. It's a very abstract concept when you go, how do I verify this thing? How do I know it's going to work? So it's helpful perhaps to have some numbers to put in context just how hard verification is. And we can see here some numbers from the scale of the Earth, scale of the galaxy, money, and then a very, very big number, 1 quadrillion, and I'll come back to that again later. And that's the number of cycles that you need, or that ARM need, to fully verify one of their modern CPUs. And that's a really, really big number to get your head around. And as a community, a RISC-V ecosystem, this is something we all need to be thinking about to build high-quality, successful products. So why is there a disconnect here? Well, as users of RISC-V, the buyers of our products, the buyers of our IP, we're expecting that CPU to just work. We want to buy a chip and just run our software on it. We want to drop out the IP into a bigger SoC and it just runs. But as individuals contributing to that community, we're unlikely to have all of those resources that the bigger companies, the ARMs, the Intels, they have to perform that same level of verification on their CPUs. But what we've also heard is, there are opportunities to work together on this. We don't have to do it all ourselves. And that's one of the great things RISC-V offers, that ability to collaborate where there's no need to differentiate. And so I'm going to talk about how we can together scale out to meet the challenges of verification for RISC-V, what we need in terms of tools and methodology to make sure we can be just as successful as all the other CPU architectures out there. It was a bit of a change probably over the last 15, 20 years, but now electronic products are increasingly defined by their software. They're not defined by just the hardware, and that software has become parts of bigger systems. So it's not just embedded systems running in isolation, but it's IoT systems, interconnected, access running on the cloud, over-the-air updates. And so instead of a device problem, it's now becoming a complete systems problem. And so, we need that hardware team working on the ISO, working on the instruction set and formalizing the specifications. We need the software to run on that and the ecosystem around it. But if we don't verify them together and prove that they're going to work, it'll all fall apart. Calista talked earlier again about the importance of portability, that promise that you can take software and you can deploy it widely across any one of these many billions of RISC-V devices. And thorough verification is a critical part of making that work. So that's our challenge. You know, we've got the ISA ecosystem, we've got the software ecosystem. Let's build that verification ecosystem as well. So back to that very big number, that 1 quadrillion, that 1,000 million. If we're trying to run that in hardware as RTL simulation, you might run a typical simulator at maybe a couple of kilohertz. So you would need to run 15,000 simulations in parallel for a year. But maybe you're doing something more advanced. You're using an emulation system. You're running on a virtual platform and running on some hardware. Maybe you go a bit faster. You get a megahertz out of it. But these boxes are expensive. You probably have only got 1 or 2 of them. You haven't got tens of thousands of them. And even then, you still need to run for 30 years of running to hit those sorts of cycles, to hit that sort of quality. And, okay, granted, embedded systems will be simpler, they'll be faster to verify, but it's still a huge amount of work you need to do, or we need to do as a community to make this a success. So let's think about how the others do it to start with. You know, there are multiple architectures out there that have already been successful, that are already very widely deployed, and you know, they have a bunch of tools that they've used to do this. But a lot of that's been developed internally. It's proprietary. They haven't been working in a community. They haven't had others to work with on these problems. And actually, they've thrown big numbers at it themselves, whether that's very large engineering teams or hundreds of millions on simulator licenses, on emulator hardware. And on top of that, they have much more control on what they're verifying. You know, we've heard already that one of the joys and benefits of RISC-V is just how configurable it is, just how customizable and flexible it is. But that also adds to that challenge of how do we verify this and how do we make sure it all works. So if we look at where that money's gone, where they've invested, you know, there's a number of things you need to do verification successfully, whether it's tools, whether it's verification IP, models, the flows themselves, they take time to develop and deploy. And beyond that, you know, I'm primarily talking about simulation-based technology, but there's formal tools and other techniques coming along now as well. And again, a lot of this has been built internally. It's not readily available through traditional EDA channels. So, you know, we've got to accept this. RISC-V does have this risk of a disconnect, and it does have this challenge around verification. So, you know, there's some data here, some facts here that show the scale of the challenge. We've touched on some of the successful ISAs, but there are many more ISAs out there that haven't stuck. So it's not, you know, we think RISC-V's got critical mass, we think it's going to go now, and there's enough people behind it, but other ISAs have been and gone. The really scary data, actually, this was from a research group report last year, is that less than a quarter of tape-outs have first-time silicon success. And that's kind of a depressing number, and it shows, you know, there's a lot of money there as well in terms of respins and fixes, and the later you find the bugs, the higher the cost of fixing them. And it also becomes a challenge for the industry if semiconductor startups no longer deliver, you know, good returns to investors. It becomes harder to fund companies and create success. So life is already hard. So let's think about then how we can work together and how we can develop common methodologies and tools and techniques that can make us all successful. You know, we've seen the diversity of the RISC-V ecosystem. There are no, you know, monsters in the room, but that means it's going to be really hard for any one player to spend the money or hire the people to develop everything they need. If you look at other business models, you know, ARM have income on the back of their royalties, Intel relies on silicon sales. Within RISC-V, we're going to have to find other ways of innovating and other ways of being efficient to be successful. So why not partner? Why not collaborate in non-competitive areas? You know, verification is a hygiene factor. Everybody needs to have well-verified cores, so we get to that state where anyone taking on RISC-V knows they're going to be successful with it. At the same time, you know, creating that activity will attract new players into the ecosystem, and we can build standards to facilitate reuse and efficiency, and I'm going to touch on one of those in a minute. And we're back to the clicker misbehaving. There we go. So yeah, as I said, verification should not be a differentiator. It should be something everyone's doing really well. So why not collaborate externally if it's not differentiating your product? Why not look at licensing commercial tools if it's not your core value proposition? So a quick bit about Imperas while I'm here. We've been going for about 15 years developing world-class processor modeling. And that was a good business in its own right. But as RISC-V came along, what we found was interesting that actually some of the customers of our models started using them for verification and started using them as golden reference models. And so for the last 5 years, we've been helping companies with their RISC-V CPU DV. And we've started working with Open Hardware Group and other members of that org. You heard from Rick just before the break about the great work Open Hardware are doing. And we've been developing methodologies to improve the verification of RISC-V CPUs in the open source world. So as Rick said, it's open source, you can download the cores, but it's using industrial rigor and industrial methodology so you can be confident of the quality. And what we've seen over the last few years is actually several levels of quality and of techniques for verification. From the kind of simple and naive, does it run a program like Hello World? Does it run self-checking tests? And these are very simple. I'll talk more about it in another talk later about what even running something like a Linux boot really tells you about how rigorously your core's been tested, and the answer is not very much. And then you move on to things like compliance checking, where you have known good signatures you might test against, or things like post-simulation trace file compare. But even then, as the processors get more complex, as you start to push into corner cases around things like interrupt, around things like debug, even these techniques aren't really good enough and become very hard to get good quality results from. And then you get on to what we're calling the proper verification of sort of more advanced techniques, where you're doing lockstep comparisons on instruction retire, and even into things like asynchronous lockstep. And that's where you can start looking into all those really interesting corners where probably there are bugs lurking. And yes, there's formal techniques as well. So if we think about what the tools you need are to create a really strong verification environment, there's lots of bits. But some of these are standard. Some of these are even wider than just the ISA. Everybody needs them, and we can leave them to other groups. Some of those are common across RISC-V, and some of those are going to be core bespoke. But there are other groups looking at these already, so things like simulators, things like compilers. We don't have to worry about those too much. But it leaves 3 areas where really we see space for innovation and working together. So those tools, you need test benches, you need frameworks, you need verification IP and good quality reference models. You need coverage. It's really hard if you start looking at, yes, the base ISA is simple, but once you've got all those extensions and customizations, you've suddenly got huge amounts of coverage to create, and those need adapting per core. And doing that's really inefficient. It's much better if you can come up with reusable IP and reusable coverage there. And this is where you need standards. So RISC-V verification interface, RVVI, this was something we came up with working with Open Hardware. And this is a standardized way to have an interface that you can drop into a core and next to it put verification IP, put golden reference models, put things around it. The standard's public, it's Apache licensed as with many things in the RISC-V space. And this makes it much easier to reuse things that you're building or bring in third-party verification IP from outside. And it then creates a hook for functional coverage as well. When you start looking at just that configuration space for a Linux-capable core with vectors, you're talking tens of thousands of lines of system Verilog to create. And that is not something you want to be doing yourself on every single core you do. It becomes something you want to reuse. And so that hooks in very nicely to that RVVI interface, and it becomes a really easy way to reuse that functional coverage. So to summarize, it's really important we're all working together to create high-quality IP that just works, that delivers on that promise that the ecosystems need. High quality means lots of resources, it means new methodologies, and it needs standards and reuse to be efficient and to scale. And as well as that hardware and software ecosystems, we think verification is the third pillar of that. So if we fail in this challenge, RISC-V fails. But collaboration has already been very successful in the hardware and software space, and we think verification is the next step in that. We think it needs to become an industry focus. Open hardware is our main focus at the moment. It'd be great to have more people along helping with that. And so with that, I'd like to say thank you very much.